Thank you, Kamal sir, for that wonderful session. Moving right along, our next session has an incredibly cool title, Flash Forward, Shaping Manufacturing Testing in the Zettabyte Era. Now, when we talk about zettabyte, we are talking about a number with 21 zeros. It sounds like pure science fiction, but there's a beautiful historical connection here. Long before the silicon chip or flash storage ever existed, ancient Indian mathematician Acharya Pingala was actually the first to map out the foundations of binary, the zeros and the ones we use today. Not only that, ancient Indian texts were among the first in human history to create names for numbers of that exact massive magnitude. If I am correct, it's about Chanda Shastra, with two numbers, Laghu and Guru, to define the syllables. So in a way, standing here in Bangalore today and talking about the zettabyte era isn't just looking into the future, it's bringing that incredible mathematical legacy full circle. To guide us through this future, we have a phenomenal leader with us. He is an alumnus of Texas A&M University, US, with over 26 years of incredible engineering experience at global giants like Western Digital, Nokia, and Jio. Today, he is leading the change as the Senior Director and Charge Site Leader for Memory Product Solutions at SanDisk. Brilliant minds, please give a fantastic warm welcome to Mr. Murtuza Mithi. May I request Kamal sir, may I request Sejal sir to please present a sapling? Yeah. To please welcome Murtuza Mithi with a sapling. Thank you, sir. Over to you, sir.
All right. Good afternoon, everyone. All right. So, before I begin, the story of data and storage is the story of civilization itself, right? From the stone carvings and sheepskins to the bamboos and papers to the more recent times magnetic and silicon storage. Each transition has been driven by one need: how do we capture more information more efficiently? Because today, we're not just storing data, we're living it. So today I'll walk you through a journey. I will walk you through the origins and innovations of NAND flash technology, to the realities of the zettabyte era, and then more importantly to the transformational role of memory testing, or in general manufacturing testing, to enable this new future. Alright, so before we begin, I'll give a little bit of an overview of SanDisk. As many of you may already know, SanDisk is a US-based company headquartered in California. It has been around for 35 plus years and has been building technology and products with a rich innovation portfolio of 11,000 plus patents. And it houses more than 10,000 plus employees worldwide today. Our employees are located in United States and outside of United States, largely in Asia, with India being the second biggest R&D center outside of the headquarters, and a large base of manufacturing in Asia and Southeast Asia. SanDisk is one of the broadest industry portfolios when it comes to memory storage. We are serving clients in enterprise data center, in client and compute with our laptops to OEM partners, gaming PCs, mobiles, automotive, IoTs, and then to retail consumers with pen drives and memory cards. So this is a diverse portfolio which is second to none in the industry. But we don't only design technology and products, we also manufacture it. We have a massive manufacturing ecosystem, starting with fab operations in Japan, where we have partnered with Kioxia, which is a spin-off of Toshiba, a prior Toshiba memory company specifically. And together, between SanDisk and Kioxia, we've pumped in billions of dollars in the last few decades in terms of flash development and fab operations. And today, nearly 1/3 of all of the NAND flash bits that are produced globally comes from this partnership. Besides the fab operations, we also have back-end operations covering testing, assembly, packaging, and testing as well, which we do both with our captive factories as well as a fleet of contract manufacturers with whom we work in Southeast Asia. So that was a little bit about the company perspective. Now let's dig into the technology a little bit. We're talking of memory as the foundation for this company. As Alan Kay said, the best way to predict the future is to create it. And this is very true in case of memory technology. The NAND flash journey began with breakthrough innovations. Pioneers like Eli Harari, who's the co-founder of SanDisk, who redefined storage architectures. Some of these started off as simple concepts, as few patents, and today these have scaled into the backbone of the digital economy. I hope some of you students, when you do this fabulous program, can come up with some of these breakthrough innovations as well. Look forward to those days. Innovation in flash has been relentless over the last 3 decades. We've gone from 2D architectures to 3D architectures. As Kamaljeet sir said, we do stack taller and taller stacks of layers. And we've also been moving in the right direction with our process nodes. And today, we are, after 17 generations of NAND flash technology, we're at a point where we have gone from storing 1 gigabit per die to 1 terabyte, 1 terabit per die, which is a 1000x increase in capacity per die. At the same time, achieving this with a 1000x cost reduction per bit. This is not just incremental changes, this is exponential transformation. While we're doing that, we've also done a few more innovations. We've gone from single level cell, which is storing 2 bits in one cell, to MLC, 2 bits, 4 bits, and then TLC, 8 bits, and QLC, 16 bits. Right? So that is trying to get more and more capacity out of the same die. And then we've also changed the way we structure from 2D to 3D. We're stacking more and more layers. These are taller and taller skyscrapers. Today, going from 200 plus layers to 300 plus in coming generations and beyond. Just to put in perspective, right, we're talking of more than 1 trillion memory structures per wafer as we fab this technology. Just to give you a visual of what that means, I'll just play this. This is how it looks, how complex it is. This is engineering at its highest level of complexity. And as some of the other speakers spoke about it, this is immensely difficult to produce in a fab with all the clean room requirements, power, water, etc. Right? So this is what we do day in and day out from our fab in Japan. Okay, the technology is good, but if you can't manufacture this in high volumes, it's no good. If you can't sell this in a market as a product, it's no good. But SanDisk has managed to overcome both these challenges in this past 30 years. With this flash technology that can scale better than many other technologies in the world, we've been able to transform industries. And you can see where we've been heading. Many of you may remember the camera rolls, the floppy disks, and the CDs to where we are today. This is from a few exabytes in the early 2000s to close to a zettabyte now as we transitioned last year. This is truly the zettabyte era that we are in now. The data is no longer just a record. We're talking of its communication, its currency, its intelligence. Do you know what comes next after zettabyte? Anyone knows what is going to be next after zettabyte? 1,000 zettabytes will be equal to what?
Yottabyte.
Sorry?
Yotta?
Yeah, somebody said it right. It's going to be yottabyte. So I think it took us almost 20 years to go from exabyte to zettabyte. Maybe it will take us less than 10 to get to the yottabyte era. Alright, I just want to touch quickly on scaling, right? Because we mentioned that in the previous slide. There are 5 vectors of scaling in 3D NAND. One is the one which we mostly hear about, this race to stack more layers and layers, and we're going from 200 to 300 and beyond, which is called as vertical scaling. There's another dimension which is lateral scaling. Now each tower can be high, but how many can we fit into the same area, which is lateral scaling. Logical scaling, which is how many bits can you have represented with one cell. So we've gone from SLC to MLC, TLC, QLC, maybe PLC in the future. And then there's architectural scaling, which is where we take the array and the CMOS, and how do we put them together on the wafer. We used to do it in a method called CNA, which is circuit next to array. But today we do it CUA. We used to do it CUA circuit under array for one generation. It didn't work out so well. But today we are in this mode where we call it a circuit bonded array, where we bond the array and the CMOS. So these are 2 different wafers produced separately and then bonded together to form the product. And this is paving the way for the next level of scaling, which we're talking about, especially in the world of AI inferencing. Right? When there's multi-bonded, multiple arrays to one CMOS, should give us the next level of scaling. Every time we hit this Moore's limit, these are the kind of innovations that are helping us scale to the next level. And finally, I want to talk about test, because test is equally important as we scale in terms of capacity. There's a dimension of test cost scaling that we need to talk about, and that's going to be the next section that I speak on. I think many people spoke about this life cycle, so I won't spend much time on it, but I do want to make one point, which is SanDisk is a vertically integrated company. We have all these elements right from chip design to fabrication to back-end testing and packaging assembly to high-volume manufacturing. It's a vertically integrated company, and that brings lots of advantages in terms of end-to-end system-level thinking to make this zettabyte era more efficient. So with that, I'll speak a little bit about the test development, because that's my bread and butter. I have been spending most of my 26 years in product and test engineering. It gave me a good memory. Mr. Kamaljeet sir put a picture of Nokia 3310 in his slide, and I was one of the engineers who worked on that product in Nokia from a test point of view. And I also helped establish the factory in Sri Perumbudur, where that was the first product that we sent out of the door. So that was with some good memories. So thank you for that. All right. So all this capacity scaling, it brings 2 problems when it comes to test. We have more bits to test. We have more test data to analyze. And so how are we going to work on these? What is the problem, first of all, with more bits to test? As we have more capacity per die, and if we have more bits per die, you should test all of it, right? Yes, we can do that, but we're going to add more and more testers. My friend in Teradyne will be very happy, but we are not sad because it's going to give more capex. So we should do something about it. At the same time, every package or every die or every product that you test adds a certain element of cost to the cost of goods. That is product cost. And today, we are somewhere around 3 to 6% of the product cost is the test cost. But the way things are scaling, if we continue to test the same way, it's going to be reversed. We may actually be spending 80 to 90% of the cost on testing and very little on the product itself. So this needs to be addressed, and this is what we at SanDisk in my team are specifically focused on. Right, so some of the strategies, some of the ways in which we're trying to do this more economically. One is increasing the built-in self-test coverage, which is also called as design for test at a device level, which means you don't necessarily use an external host, you don't use external communication while testing, try to do it within the device itself. This helps with test time. It helps finish your test faster. Then you also observe that maybe not all bits need to be tested. Right? Why are we testing? We're testing because we're not so sure about the process. Right? There may be process defects. We don't usually test in manufacturing for design. It's usually for process defects. So we don't expect every bit to have a problem. So how can we do this more selectively? Do we need to test all bits, or do we need to test all bits with the same level of coverage? That's an aspect that we are focused on. And then in terms of testers, right, we want to develop the next set of testers, which are of course lower cost, but with high level of parallelism, so that eventually the cost per dot is more economical. And we want to have these testers which are more modular, which can allow us to test across our different fleet of products, different form factors, and different generations. Right? We don't want to change the tester as we go from one generation to another. So that's another focus area. We also use a lot of machine learning in terms of predicting the failures to reduce the number of tests that we do, and that is through data analytics and through collection of data. I'll speak a little bit more about that in the next slide. And then if we really have to test, where should we test it, right? I think it's basic, but I want to realize it's basic, but we usually forget this into day-to-day humdrum. We want to test it as early as possible, so shift left, right? We want to test it, preferably everything at the wafer level, so that if it's a failure, the cost is minimal, and we don't end up scrapping more dies or more products at the back end. So these are some of the ways in which we are trying to cover the test strategies. How to reduce the manufacturing lead time, how do we reduce the tester costs, how do we save capex. If we do all of these three, those two vectors that I spoke about as problem statements are getting better as we go along. The second part, which is the test data to analyze. Test data is exploding as these capacity per die, per package, or the drive level increases. We're talking of, as an example with SSD test data, 150x increase in the test data itself, right? And this is huge, right? What is the problem with that, right? It's leading to a data overload. We have all this data at our disposal, but we don't know where to start. Sometimes we don't know where to look. So we're not even sure if all of this data is meaningful. In some of the analysis as we go through, we realize we're testing the same thing over and over again in different insertions, at the wafer level, at the package level, at the drive level. Is that really needed? Are we over-testing? Sometimes we even realize we have tests forever in our flow, and we never see any failures in the entire lifetime. So are these tests really needed? So these are the ways in which we're trying to make our test setups a little bit smarter, so that we can make it more efficient, less overload of data for analysis at a later point of time. And then very importantly for machine learning, right? We started our journey of machine learning maybe almost 10 years ago. And what we're seeing is there's a specific limit that we hit in terms of prediction accuracy, especially the failed prediction accuracies. And for many years we thought it's a problem of the machine learning algorithms, but we realize it's not necessarily true. It's also a function of what data you're collecting, what data are you generating. So we need to start really looking at how are we generating the right data to be able to enable the machine learning with better prediction accuracies. So with these kind of points in mind is what has been our focus in terms of test data. We want to capture and process richer data so that we can improve those prediction accuracies. And if we can do that, we should be able to remove or at least reduce some of these physical insertions that we have in our test flow today. We also want to be able to improve data logging. We want to collect the right data, but we also want to be able to log it before we can analyze it. And sometimes we do hit the boundaries of what we can log because memory is constrained. But in this case, our device itself is a storage device. So we're trying to see if we can log some of the data in the memory itself while it's being manufactured and be able to use and leverage that for data analytics eventually. And then a lot of vendor collaboration with our test vendors, especially to be able to do more in terms of being able to clock in and clock out this data much faster, be able to do inline inferencing while we are in testing. A lot of that needs a collaboration with the vendors in terms of the tester infrastructure. So these are some of the things that we are focusing on. So what does the long-term view look like? And what are we envisioning at SanDisk from a test perspective? And I'm sure most of you have seen the movie RRR. Yes, no? Many of you should have seen RRR. Yeah. So we're not motivated by the movie itself, but by the 3 R's. Right? So the first R is to reduce. So we're trying to see if we can go from many to single insertions. Right? So we have these 3 broad stages at where we do the testing. One is the wafer level, one is the package level, and then one is the system level. But at each stage we have multiple insertions. And we're trying to see if we can get down from the multiple insertions to single insertions at each of those stages. So that's the first R, which is reduce. The second R is basically remove. Right? And how we plan to do that is with machine learning and real-time analytics. But for that we need that richer data. And which is where we're trying to do a lot more data, a lot more testing, capturing analog parameters. In the past, we were more doing pass-fail kind of tests. We not necessarily cared about the actual test data. We were losing that. We're trying to capture that because that data has a lot more value in terms of prediction. And when we do that, we hope to see the prediction accuracies get closer to what we want. Ideally, we want it to be 100%. We want to predict everything, right? But that's not going to happen. But how do we get to those 80%, 90% prediction accuracies? That relies on this analog data that we can store as part of the testing. And then finally the last R, which is replace. Right? So if we have to replace some of these test flows, we want them to be more ultra efficient. I kind of mentioned that we have this smart way of collecting the data and analyzing it to see what remains, what doesn't remain. We want to have massive test parallelism in our new testers. They should of course be low cost, low power, and be able to have AI processing capabilities in the tester itself. We touched on it, so that was good to hear. And if we can do all of these 3, we are surely ready for the zettabyte era with being economical at the same time. Right? So finally, what's next? Right? I don't want to read this slide, but there's a theme behind this. And yesterday, some of the things we did laid the foundation. Today is testing times, right? It's testing our limits. We're already hitting zettabyte era. Tomorrow, especially with this AI boom, is going to reward those who can rethink the system end to end. And I think SanDisk is best positioned because of this vertical integration within the company. And we're really rethinking it end to end. How can we not only design, how can we manufacture, how can we test the product? All that is being considered in our next generation of technology. Right, so this is the final slide. The future of storage and compute will be defined by, one, of course, we continue to have the next gen of memory architectures. We've done 17 generations so far, we'll probably do another 17. And while we continue to serve the market with higher capacity, higher performance products like SSDs, we'll transition to QLC. Today, majority of our products are still on TLC. We'll transition to QLC. And we have something called high bandwidth flash, which is in the works, which is supposed to be a much better memory for the AI world. And it comes with a lot of advanced packaging schemes that will need to be implemented, such as TSV. So there's a lot of focus on that. And this together is what is going to enable us towards this intelligence at scale in the zettabyte era. And manufacturing testing, as you know, sometimes is in the background, but with this, with the world we are headed in, it no longer remains in the background. It's truly in the forefront and is a critical enabler for the zettabyte era. Thank you so much. That was my last one. So yeah, I can take some questions. I think I have some time left. Sure. Yeah.
Yeah, thanks for the briefing and really enjoyed it. My name is Srini Subramanian. I come with close to about 30 years of industry experience and recently started my own startup, ECEDA Technologies. It's very interesting to see I'm not from a hardcore semiconductor manufacturing, but I come with the electronics and basic physics and engineering background. So when you talk about the testing part of it, that's a process capability. You are using a lot of machineries and process. So is there any statistical way of making sure that your system is capable of producing error-free or defect-free components? That is one part. I have two questions. Sorry about it. That is one thing. Second thing is, this is what ECEDA was really. It is not I'm promoting my company, but then based on my experience, what I found is that the intelligence or the decision making is on a real time is missing in most of the industries. So I think you rightly pointed out that instead of collecting the data and then feeding it into a testing system and then getting back to it, rather than collecting the signal right from the source of the defect on a real time basis, is that something which you can think of, or that is what our intelligence system is? We have created a platform around it actually. Rather than doing little postmortem, rather than real-time collection of signals. That's how I'm just thinking. So what is your opinion about it? Yeah, that's not my question. Sorry about two questions in the same.
No, that's okay. So first question, if I understood you right, can we eliminate the defect? That would depend on the process tools that we use, right? So the testing comes into picture because we think that there's going to be a defect, right? So that's a different set of people that should be working on how can you reduce the defects, especially in terms of process, right? On the second part, what you mentioned, right, which is very true. That's exactly what we're trying to do. How can we get the decision making done closer to the step that creates the defect, not 6 steps later and which translates to months later, right? Because these steps are not sitting next to each other. Sometimes it traverses countries and goes to another manufacturing setup before you can detect the failure of a step that happened many months ago, which leads to another kind of problem of inventory build-up and whatnot, right? So you do want to have real-time and inline decision making. The challenge with that, and of course we have made some inroads, but I can't say that we have cracked it. The challenge comes with the availability of data, the sanity of that data, to be able to apply real-time inferencing, right? So I don't know if I'm making sense, right? But if you can do that, then inferencing is very easy, right? You can always predict. Right? Machine learning models are very advanced. But what we've seen is that some of this data itself is not available or it's not clean enough. It has to be sanitized before you can do those. And of course, sometimes it's very how do you say, business-wise, it's probably set up like that, because if you're not making that within your own company, let's say in some cases we do our packaging, for example, with a third party. They may not give us the data for the tools that they use, right? Which means then we're limited. We really don't see that data at the right time, and then we have to rely on our testing when it comes to our factories to make the decision. So it's a mix of both. But always the step is in the right direction, which I think you also are aligning to, is we don't want to actually do tests at a later stage. We want to do it right at the point where the failure can be generated, right? So
yeah, absolutely. On the first, thanks for it. On the first question, I'm not expecting a zero defect. Maybe we talk about Six Sigma level and that kind of a thing. So that is both machine as well as the process capability play a very key role in making sure that we are killing that defect right from the origin of the thing itself. But having said that, nothing is defect free, because even Six Sigma, when we talk about it is not defect free. So I'm just wondering whether you are deploying such concepts in semiconductor manufacturing places, because that's what I'm interested.
Yeah, of course. I mean, Six Sigma concepts for sure. In fact, process fab is like the first place where we apply Six Sigma concepts more than anything else.
Okay, sure. Thank you very much.
You guys can discuss more.
Yeah, we can catch up. Okay, I think I'm holding you guys between. I mean, I'm between you and lunch, so.
We have one panel discussion.
Oh, we have one more. Oh, sorry. Then we have to stay a little bit longer. Thank you.
Very interesting panel.
Thank you.
Murtuza sir for that wonderful session, walking us through various models of memory models of SanDisk, its future perspectives and everything. Thank you so much for the wonderful session. May I invite Vishal Shah sir to please felicitate or present a memento to our Murtuza sir. Over to my co-host Rajila for the wonderful panel discussion ahead. Thank you.